Okay, so that finishes up the slow and cautious part. So now we need to make a proper algorithm. Formalize this by putting in a pseudocode the way that we're going to directly tell the machine how to do it. And we already went through that slow, thorough process of analyzing the problem and putting our thoughts together, so it should go fairly quickly from here on out. So we have those keywords. We need to prompt the user for some information to start with. So our keyword for that was write. So we're going to write, we should probably go with some polite ones. Please input the required dose. And always be very thorough in your prompts. If the user doesn't need a thorough prompt, they're going to skim it and skip over a bunch of it. But if they do need to know exactly, they might need those instructions. So make sure you're very thorough. If the user doesn't need the details, they'll skip over them. I'm sure everybody knows how that goes. You see the instructions and you know what to do, so you just skip reading them. Whereas other times we see the instructions and look at the inputs and I'm not sure what to do. So then we go back and read the instructions. So make sure you're very thorough with your prompts. Please input the required dosage. And then we need to set that somewhere. So then our next keyword is going to be set some variable. So we'll set script equal to that input. Whatever the user puts in. I guess we could add here, do not include the MG. So don't include the units. So in this case, the user will just type in 75. And then we'll know that's in milligrams. And then we need to know what the bottle has. So again, write, please input the please input the medication value. I might think of better words for that. I guess this one's not really a question. I could put colons here. I always like to put a colon or a question mark on a prompt. That way the user knows we're waiting on them. Please input the medication value. Do not include units. No, do not include the units, then a colon, so the user knows we're waiting on them to give input. And then we'll set, available equal to that input. Then we can do our calculation, and our very next lecture is going to be math. So I hope you're already familiar with the fact that machines can do math. We can use them like a calculator. If not, when we're programming, we can perform calculations. That is our very next lecture. But we can do things like multiply and divide. So we need the conversion to get between milligrams and milliliters. And let me pull something up to write out how conversions, if you haven't seen that in a while. So just real quick here, in case you haven't seen it in a while, a recap on how we perform conversions between different units. In high school, you probably learned a really hard method. There's an easier way to do it, what humans have been doing for thousands of years, and then at some point in the 1960s, in America and Europe, they decided to take that out of the elementary and high school education and do a really hard way instead. But the easy way that has been worked for thousands of years is phasing back in. We do what's called dimensional analysis. That word analyze again, a form of analyze. We're going to break down the dimensions of our problem and look at that. Or another way to put it is we're going to do the math with the units instead of the numbers. So a quick, easy, general process that'll work for everything is we have our rules for fractions. The big one is if we have similar things in the top of a fraction and bottom of a fraction, we can cancel and reduce fractions. Hopefully you remember that part. So we can set things up that way with our units. So in the case of this example, the doctor told us to take 75 milligrams. 75 milligrams per 1 dose. So that's the units we need. So we need to get rid of milligrams and turn that into milliliters. So if we ignore our numbers and look at only our units, in order to cancel that, we could use that property of fractions where if milligrams is in the bottom, we can put it in we can cancel that out. So we need to know, is there a way that we can put that in a fraction? Like, do we know anything where some number in milligrams is equal to some number in milliliters? And we do for the problem statement, right? In that problem statement, I wrote 15 milligrams in 1 milliliter. So that's an equivalent statement. They're equal. So if we write them as a fraction, even though they'll look different because of the units, that's still the same thing on the numerator and denominator. So it's a 1, and multiplying by 1 doesn't change anything. As long as we can say this along the way, we can just make up a fraction. And then we do our math with the units instead of the numbers, because those milligrams are going to cancel. And we're left with milliliters per, we're left with the units of milliliters per dose. Then we come back and do the numbers. What did I say? So 15 milligrams in 1 milliliter. So if we multiply that out, so I'm going to write the steps here and come up with a simpler formula to go into the computer. That way we don't have to go through the whole process. So we multiply 75 times 1, which isn't going to change anything. And then 1 times 15 doesn't change anything, so we don't really need to multiply. We can just divide the milligrams in the script, milligrams in prescription. That's the wrong word, so I'll abbreviate it a little. The milligrams in the prescription divided by the milligrams in the medicine. So that'll be the formula we need to do this conversion. And our general process to find it, the generic catch-all one is going to use b-dimensional analysis. Because we can always find some sort of equivalent value we can put in a fraction, and then use our values of our properties of fractions to cancel out the units we want. So do the math with the units instead of the numbers. It's called dimensional analysis. And that gets us to a formula. So the milligrams in the prescription divided by the number of milligrams in the medication will leave us, that divided by that, will leave us with the number of milliliters in the dose. So that's the quick pass at how we put together conversions. Now that we have our formula, we can put that into our pseudocode here. So we'll store it in a value so that we can concatenate it into some nice looking output in a moment. So we'll set some variable, I'll call it dose. Might as well spell these out. Dosage. Well, typing's quick. Don't be lazy with typing. On the board, I often abbreviate things because right now on the board, it's kind of slow and takes up a lot of space. Same thing on paper. But typing is really easy. So don't be lazy with the typing. Go ahead and spell things out and make it very clear what they stand for. So we'll set dosage equal to prescription, C-R-I-P, prescription divided by, and a forward slash will be our symbol for division. We're going to see that in the next lecture more formally. Prescription divided by available. Medication might be a better word. That's what I used on the board. So come over here and change this to medication. So we'll get the milligrams in the prescription, get the milliliters and put the medication value. I can change this prompt a little and be precise about what we want. Get the milligrams per milliliter in the medication. Do not include units. There we go. That's very clear and precise, telling the user exactly what numbers we need from them. You want to watch for that. And again, notice how I'm jumping around. The computer needs this to be in a specific order. And that order might not match the way we think. So a lot of times when I'm putting algorithms together, I end up jumping around back and forth a lot and do it in the order that I think in, and the final result just needs to be in the order the computer needs it in. Alright, so now that we have the dosage, we're ready for the output. So we're going to write to the output take plus dosage plus milliliters each time. So we'll find out how many milliliters to take per dose, and then concatenate that into some output. So there's our algorithm. So let's go over to Raptor and clean and code this up. So I've made it a point not to close Windows Explorer here for a moment so that these would be in order as I was making these scenes. So this is our process. So the problem statement, then analyze the problem, design a solution, and then develop an algorithm. And then after this, obviously the scene that is currently being recorded hasn't been saved yet, but after this comes code up the solution. But coding is just the tedious, busy work at the end. This is our work for software development, the thinking. Or if we want to use some more fun terms to use, the plotting and scheming and conspiring. Just more interesting words to use, but it's a planning and a thinking thing. I've alluded to it several times. We can have a computer generate the code for us. And even if we want to type it ourselves and type everything ourselves, that is just the tedious, busy work at the end. The work is coming up with a plan. And so at this point, please focus on these steps we just went through for developing a plan and an algorithm. And as you focus on it here at the beginning, it's going to become more second nature, become almost instinctual. So then you won't have to put so much focus into it. It's just going to flow out of you. But at this point, you should probably focus directly on these steps. And then the coding is just the tedious, busy work at the end. So let's go do some of that. So over here in Raptor, got Raptor open. I'm going to go ahead and hit tile vertical just to kind of set it up to have space to work with and read all the outputs. Okay, so let's get started with this, coding this up. So I have the algorithm we just put together over here on the other screen, so we can refer to that. And the first thing I'm going to do is go ahead and save this, because I always forget to do that, or usually forget to do that, and then Raptor interrupts me in the middle of something. So I'll go ahead and save it so I don't get interrupted. So the first thing we need to do is prompt the user for these values. So some sort of message telling the user what we want, and then we're going to put that in whatever they give us into a variable called prescription. So we do that with our input box. I'm going to click that, drag it over, then double click on it, and some sort of a prompt. What did the doctor say? No units. And put that in a variable called prescription. So we can get that from the doctor, and I changed it up to express the point. When I'm grading, I usually feel like I can tell whether the coding was done first or the algorithm was done first, because I know in my stuff, the only time the code ever matches the algorithm is if the code was done first. Because the algorithm, there's going to be some change. Right, the algorithm, and then things get changed when coding it up. But that doesn't seem to happen the other way. If the code's done first, then the algorithm the pseudocode seems to be an exact copy of it. Oh, whoops, then another input. So then we need to get what the bottle says. So once again, an input, and if it's highlighted over here, we can just click at the spot on the flowchart we want it to go. So what does the bottle say? And again, no units. Kind of abbreviating it here. There's probably better ways, more clear prompts to put there, better ways to do that. And I'll call that medication. So now that we have our variables, that takes care of the first 4 lines in our pseudocode. We get those numbers from the user and store them in these variables. Now we're ready to do the calculation. And remember, that's going to be an assignment box. Let's bring that over, and we're going to assign a variable called dosage. A variable called dosage, the value of prescription. And notice how that's coming up in red there. I'll go ahead and show this. When I started typing it, it predicted the variable. So it works here. If I push tab, it'll fill that out. It'll go ahead and insert it. And it's a good idea to let the computer type it, because the computer never makes typos. Or maybe I made a typo when I typed prescription the first time, and that would cause a problem. So it's always a good idea to let the computer type it. Divided by medication, and off the first 2 letters it predicted the right variable, so I'll just hit tab to let the computer finish typing it. And in Raptor, that doesn't work everywhere, but as much as that doesn't work on the outputs, but it'll work in the calculations. So you want to do that as much as you can. Let the computer do the typing. So that gives us the value, and then on our algorithm, the last line in the pseudocode is we want to put together an output with that. And we don't want to just throw a number up on the screen with no context. So make sure your outputs are labeled and clear what's going on. So in this case, take plus whatever's stored in that variable dosage plus milliliters each time. So that should be the whole algorithm. So let's run this. I slowed it down, not quite it's still pretty fast, but slowed it down just a little. And remember to keep an eye on the watch window as it runs to make sure all the variables look correct along the way through. What did the doctor say? So the doctor said take 75 milligrams. And what does the bottle say? The bottle said there's 15 milligrams per milliliter. We'll do the calculation and throw up the output, which looks like it's a little off. Milliliters, well, the symbol for liters is a capital L, so I should change that. And this is a process called debugging, which goes back to the early machines. On one of the early machines, might have been the Harvard Mark 1 or one of the UniVac machines. I'm not sure which one off the top of my head. I'd have to look it up. But I was getting ready to point you towards looking something up. On one of those early machines, it wasn't working right. And they had to take the machine apart and figure out what was wrong with it. And it was Grace Hopper who did that, took it apart, put it back together. And, took it apart, found the problem, which was a moth had flown into the machine and shorted out a circuit. So she pulled the moth out, and it was a military thing, so she had to write a report. And in that report, she said the problem was she had to debug the machine. And that's the term that's stuck around since then. We have to debug our code. Take it apart and pull the moths out. So it was Grace Hopper that did that. And if you aren't familiar with that name, you should be. So go look that up. Right like it sounds. Grace, Grace, Hopper, Hopper. And yeah, if you're getting into computers, you should know her name. And and kind of look into her some, because she's basically one of the people that gave us these things. So, lost track of my train of thought. Oh, yeah, debugging. So, that should have been a capital L, so I'm going to run that again, see if that fixed it. I'm also going to turn the speed back up. What did the doctor say? Doctor said take 75, and the bottle says 15 milligrams per milliliter. Well, that fixed that one. And I got the punctuation on the sentence, but a sentence should start with a capital letter, which is another thing. Always fix one bug at a time. Don't try to fix multiple bugs. In more complex examples, the bugs may be related. So if you try to fix two at a time, you inadvertently create another one. So always make sure you just fix one thing at a time. Fix one thing, test it. Fix one thing, test it. Always just, simpler problems in the big problem. There's several, there was problems with this output. So analyzing that, breaking it down into pieces, there was a problem here, and there was a problem here. So fixing them one at a time gets us back to this, just one little piece at a time until it's fixed. So keep that in mind. Well, looks like that's some good output given the right numbers and everything, but this filled up awful quick. We have this button down here to clear it, so we could hit that every time, but there's a way we can put that clear into the code. So let's look at that next and clean up this code. Look at ways to clean up this code. Even though it's only 4 pieces, we could organize this a little more. So let's do that now. So first off, let's avoid hitting this clear button every time and just have the code automatically clear what's there. So I'm going to run this a couple times just to put some numbers in there. And make sure you use numbers you can check. So that last time, 22 and 44, well, if we divide those, we should get a 2. So make sure you can check the numbers and make sure it's giving the right numbers. But the thing we were talking about with the 4 constructs, there was the invoke a process construct, invocation. So in Raptor, that's going to be this one here, the call box. So we'll just drag that over. And it's a little different than the standard UML symbol, but the people that put Raptor together thought this conveyed that information a little clearer. And this was built back in the 90s, so screens weren't in the best shape. So having extra wide lines down the side here on a lousy screen could easily be confused with this one. Or if the printer, if there's like fresh ink in the printer and it smudges a little, those could be confused very easily. So they come up with another symbol that still conveys the information accurately. So not the official UML symbol, but we can tell what it's doing from the diagram. So this is the symbol to invoke another process. And if you wanted to break it down, you could say we've already invoked processes, because like this input box here, we didn't write code on how to get an input. Same thing with an output. We didn't write the code for how to output stuff. We just invoke those processes. So there's lots of layers of invocation. But for the direct layer, we have the call. So to do that, we can call some pre-built methods. So I'm going to start typing, and notice as soon as I hit a C, it tried to predict what I was going to type. The first one here, clear console. Well, this is the console output, so that's the one I want. And if I try to hit tab, though, it doesn't, like the output box the tab won't work. So it's only certain places in Raptor that we can use that auto typing, but it's a good idea to use it when we can. So I'm going to hit clear console. So the first thing this program does now is clears whatever's already in that output, runs through it, and then spits out the output. So that way we don't have a whole bunch of extra stuff. So now if I run this again, from our problem statement, the doctor said take 75 milligrams, and the label on the bottle says there's 15 milligrams per milliliter. So you can see first thing it did is cleared all that output, so we don't have to keep hitting this button, or we don't end up with a mess of stuff over here to dig through. So that's a good start for cleaning things up. It's just clearing the output every time. Make sure we only have the latest run there. The next step is we can use that same invocation process, invocation feature to move these to subcharts. So let's do that. So up here, make sure you're in intermediate mode. I think this first one works in novice mode, but we'll also be looking at another one before long. So make sure you set this to intermediate mode. And you just right click up here by the tabs, and we have these two options, add subchart or add procedure. We'll look at procedure later. I'll go ahead and click on the box. So procedure is a completely separate thing. So if we create a variable in our main chart, we can't access it from a procedure, and vice versa. If we create a variable in our procedure, we can't access it from our main chart. We pass things back and forth. That's what these input-output options are. We'll look at that one before long. Our other option, we right-click here, or right-click here on the tab, sorry. Right-click on the tab, add subchart. So this is, it's like we don't really leave this chart. So any variables we create in our main or any subcharts of the main, we still have access to, because we're just organizing it onto different tabs basically, so that it looks nicer. It doesn't take up tons of space, and we can organize it a little better is really what it is. But it's still the same chart. So let's see, the first little subchart, we can make an input chart. So I'm going to call this inputs. So that'll create another one. And then what I'm going to do is I'm going to select both of these and then push Control X to cut them. Come over here, click where I want it to go. So you have to click the arrow first where you want it to go, and then Control V to paste it. So I just moved those inputs over to this little subchart called inputs. And then in the main, in the spot they were at, I can bring in that invocation function, and I want to call that. I want to call inputs. So now I'll slow it down when we run it. It's going to do the same thing. So it goes to the clear console, then when it hit inputs, it jumped over to this other tab, which is really still associated with it. So any variables that we create here, we still have access to in our main tab. So the doctor said 75, and the bottle says 15. And then it goes, so after it finishes, that's the invocation. It leaves our sequence and comes back to it. It can leave and come back. And so now all the input stuff is organized on its own tab, instead of just being in that mess of boxes on the flowchart. And we could do that a couple more times. Right click on one of the tabs again, add another subchart for calculations. And again, I'm going to come over here, select, well, we just have one this time, but you can do a box select, so you just click and drag around stuff. Or select that one and hit Control X to cut it. Come over here, select where it's going to go. So click there, and then Control V to paste it. And then back in our main, we'll just call that. That's the way I usually do it, the right click and then bring that in. You also have the alternative of bringing in a callback and, well, maybe another subtab called outputs, just to organize everything nicely. So we want to call outputs. When I hit done, it doesn't exist. Do you want to create a new tab? Yes, and this box will automatically create a subchart, not a procedure. So if we hit that, it created it, move that over there. So then we just cut this from our main and paste it in the subchart. So you can see it's just a little more organized. If there's a, when we go to debug it, if there's a problem in the inputs, we can go to that tab, that subchart that has only the inputs. So we're only looking at that and don't have all the other stuff in the way. Or if there's a problem with the calculations, we can go to that tab and just organize everything nicely, and it should still work the same. It just jumps between them. I'll slow that down a bunch and run that again so we can see it jumping. So it goes there, then it jumps over to that other tab, 75 and 15. Then it goes back to where it was and jumps to the next tab, does that, jumps to the other tab, and when it finishes it, it comes back to the main. So it leaves and comes back to our sequence. That's what invocation is. So that's subcharts, kind of a way to organize your code. Makes it a whole lot easier to debug. And then this clear console one, you're probably just going to want to put that in every example to get all the junk out of here so you can tell what the output is from a particular run. So let's step back over to the board and wrap everything up here real quick. If you have any questions about the example, let me know. So this is how the lectures are going to go for pretty much the rest of the semester. We're going to talk a little bit about concepts, and then we'll see those concepts applied in an example. And keep these things in mind. Right now, keep them at the forefront of your mind, and let them move back and become instincts as you do more and more examples. But for now, focus on them, analyzing the problem, looking at it analytically. That's one of our main two types of knowledge. Analytical, which is one way to think about it, is the definitions. The pieces making up that. How is it defined? The other main type of knowledge is going to be synthetic. That's building something new. Opposed to definition, synthetic knowledge is often taken as personal experience. The outcome of our personal experiences, what we've learned from our experiences, instead of just memorizing the analytical definition. Or if you're like me and a fan of British empiricism, you might just go ahead and say those are the only types of knowledge. And anything else is sub reptio. Or as a couple of Scottish philosophers put it, nonsense that we mistook for being knowledge. That's British empiricism. It's either analytic, synthetic, or subreptio, mistaken for knowledge. But there's different thoughts. Those are our main two, analytical, synthetic, and most of your school stuff is analytical knowledge. So that word's going to show up in every class, and this is the underlying meaning of what analysis is, or it's the definition. And for developing software, writing programs, problem solving, we're going to analyze it with our 4 constructs for problem solving. And finally here, since they didn't show up last week, I want to remind you about our main picture for the week, right? What we're doing this semester is coming in, you at least knew computers had inputs and outputs. And then in between stuff happens, right? We have sequences, and I'll just do some sort of sequence going to volatile storage. And we added a new symbol here. I'll use the one Raptor's using there. Then we can invoke something or jump to another process. A little bit more of a sequence here. I don't know, a couple more variable spots like we're doing math. Our outputs over here. So what we're doing is filling in this picture. And the other one I'm going to use a lot, didn't show up this week, and didn't show up last week, so just reminders, our stack heap diagrams, where we're kind of analyzing what's going on inside the computer. Think of the stack as our code, and the heap is memory or CPU. What the actual processing part of memory, because I shouldn't put CPU because our code is going to be passed through the CPU. That's the point of this. But our code, the foreground, and then the memory in the background. And if you wanted to, you could add these, because And the input is going to come into our code, and the computer's going to put everything together and throw the output on there. So that's kind of tie those pictures together to help build understanding. If you're a visual-based learner, but I want to at least remind you about our two main pictures. Our main picture for this semester is we're filling things in, and this is the picture I'll often use to break down what's going on in an example. But most of the lectures are going to be like this: a concept, then an example to see the concept applied. And yeah, try to focus on these things as you do the problems for this week. So as you solve the problems for this week, break those problems. They're complicated. Break them up into complex collections of simple problems, and then go with each problem one at a time. Each simple problem by itself, and keep the four constructs in mind, and focus on these things as we get into developing software.